Our universe is a strange and wonderful place. It's even stranger than that, actually. It's stranger than we can imagine. Why? Because the universe plays by two sets of rules, classical physics and quantum physics. Classical physics governs the big stuff, the familiar world of falling apples and orbiting planets. Quantum physics, however, reigns supreme in the microscopic realm of atoms and their even tinier constituents. The two seem incompatible, yet both are essential to understand the universe's intricate workings. Imagine a game of billiards. You hit a ball. It moves with a specific speed and direction, eventually colliding with another ball, which then reacts predictably. This is classical physics in action, predictable, deterministic, like a well-oiled machine. Isaac Newton's laws describe this world beautifully. The planets majestically dance around the sun, locked in their orbits by gravity, their movements predictable centuries in advance. Classical physics is the physics of everyday experience. It works and it makes sense, but then we venture into the quantum realm. Quantum physics is where things get truly bizarre. It's a realm that defies our everyday experiences and challenges our understanding of reality. Imagine a single billiard ball being in multiple places simultaneously, as if it can exist in different locations at the same time, or suddenly disappearing and reappearing somewhere else entirely, as if it can teleport from one spot to another without traversing the space in between. This is the counterintuitive world of quantum superposition, where particles can exist in multiple states at once until they are observed. Particles don't exist in definite states. Instead, they exist in a haze of probabilities described by what we call a wave function. This wave function encapsulates all possible states a particle can be in. Then there's the Heisenberg uncertainty principle, which states that the more precisely we know a particle's position, the less we can know about its momentum, and vice versa. This principle highlights the intrinsic limitations in our ability to measure quantum systems. It's as if the act of observation itself influences the very nature of reality, collapsing the wave function into a single state. This is not just theoretical mumbo-jumbo. These principles form the foundation of quantum mechanics, a field that has revolutionized our understanding of the universe. These strange quantum effects have been experimentally verified countless times through meticulous and precise experiments conducted by scientists around the world. Quantum physics is very real, even if it defies our everyday intuition. It has practical applications in technology such as quantum computing, which promises to revolutionize the way we process information. Classical physics is deterministic. Knowing the initial conditions of a system, like the speed and position of our billiard balls, allows us to predict its future with remarkable accuracy. This predictability is a hallmark of classical mechanics, where every action has a clear and calculable reaction. The universe, in this view, is a giant clockwork mechanism, ticking along a predetermined path. Every gear and cog moves in a precise manner, leaving no room for randomness or uncertainty. Quantum mechanics throws a wrench into this neat picture. It introduces a level of unpredictability that classical physics cannot account for. Instead of certainty, we have probability. Quantum mechanics suggests that particles exist in a state of superposition, where they can be in multiple states at once until observed. We can only predict the likelihood of a particle being in a particular state, not its exact location or momentum. This probabilistic nature is a fundamental aspect of quantum theory. This fundamental randomness at the heart of reality is deeply unsettling to many, but it's a cornerstone of quantum theory. It challenges our understanding of the universe and forces us to rethink the nature of reality itself. This difference in determinism versus probability is one of the most significant clashes between the two realms of physics. While classical physics offers a predictable and orderly universe, quantum mechanics presents a world full of possibilities and uncertainties, making it a fascinating and complex field of study. Why do we need two sets of rules? Because both classical and quantum physics are incredibly successful in their respective domains. Engineers use classical physics to build bridges, airplanes, and skyscrapers. Astrophysicists use it to predict eclipses and the motions of celestial bodies. Quantum physics, on the other hand, underpins our understanding of chemistry, materials, science, and the workings of stars. It's the foundation for many modern technologies, including lasers, transistors, and medical imaging devices. Our technological world wouldn't exist without both of these pillars of physics. The biggest elephant in the room is the glaring incompatibility between these two theories. Physicists have long dreamed of a theory of everything, a single elegant framework that could encompass both the macroscopic and microscopic realms. One leading contender is string theory, which proposes that the universe isn't made of point-like particles, but of tiny vibrating strings. Different vibrations would give rise to the different forces and particles we observe. However, string theory remains highly speculative and lacks experimental verification. The quest for a unified theory of physics is one of the most significant challenges facing modern science. Quantum physics doesn't just challenge our understanding of the universe, it challenges our understanding of reality itself. It forces us to rethink the very fabric of existence and the principles that govern it. What does it mean for a particle to be in multiple states at once? This phenomenon, known as superposition, defies our classical intuition and suggests that particles can exist in multiple places or states simultaneously. Does the act of observation truly influence reality, or is there something deeper we're missing? The famous double-slit experiment hints that particles behave differently when observed, raising questions about the role of the observer in the quantum world. These questions delve into the very nature of existence and consciousness. They challenge us to consider whether reality is a fixed entity or a fluid construct shaped by our perceptions. Some interpretations of quantum mechanics, like the many worlds interpretation, propose that every quantum measurement causes the universe to split into multiple parallel universes, each representing a different outcome. This idea suggests a vast, branching multiverse where every possibility is realized. While fascinating, such ideas remain highly speculative. They push the boundaries of our understanding and invite us to explore the unknown. Quantum physics forces us to confront profound philosophical questions about the nature of reality and our place in the world. It challenges us to rethink our assumptions and consider new possibilities about the universe. The clash between classical and quantum physics highlights the ever-evolving nature of science. It reminds us that our understanding of the universe is always incomplete and that there's always more to discover. The quest to reconcile these two pillars of physics is a journey into the heart of reality itself. It's a journey driven by curiosity, a thirst for knowledge, and perhaps a touch of awe at the sheer strangeness of the universe we inhabit. The answers we seek may ultimately revolutionize our understanding of the cosmos and our place within it. The universe is stranger than we imagine, and the journey to unravel its secrets is just beginning.